Alright, so the purpose of this video is going to be to learn how to solve for truss force members using method of joints. So what you see here on the screen is we have this simple truss, which is supported by a pin support on the left side, a roller support on the right side. We have a 500-pound load in the, not quite the middle, so it looks like it's 2 feet from the pin support, and then the roller being 5 feet from the pin support. So you can see here I have some of the steps listed. We also have some assumptions that we have to deal with here. So the first assumption is that all loads are applied at the joints, which means that we cannot have a load like out in the middle in between two joints. That means we wouldn't be able to account for the bending that occurs in that particular member. The next thing that we're looking at is, and because of that, members carry loads along their centroid. So that means loads can only be in tension or compression. They cannot be twisting. They cannot be bending. We're focused on tension and compression here. And then we have this equation here, 2J equals M plus R. So we're assuming that trusses are statically determinate. And that simply means that we're able to account for all of the forces that are inside the truss. So the variables that you see here, 2J, J stands for the number of joints. And so on our truss here, we have a joint up here at the top. We have a joint here where the pin is, where the load is, and then so basically where all the members connect. And we'll go ahead and label those joints. So we'll call this one joint A, we'll call this one joint B, and then C and D. So we have a total of 4 joints, so our equation up here is 2 times 4. And then M stands for members, the number of members that we have. And so we have member AB, we have member AC, BC, BD, and CD. And so that means we have 5 members. So we'll go 5 members here, plus the number of reactions. So the number of reactions, the pin support, if you remember from last week, the pin support has a reaction force in the X direction, and it also has a reaction force in the Y direction. So therefore, that one has 2 reactions, and the roller support only has a reaction force in the X or Y direction, depending on the configuration of the truss. And so this truss is sitting on the ground, so the reaction force for the roller would be in the Y direction. So that would be 2 reactions for the pin, 1 reaction for the roller. So that's going to give us 5 plus 3. So 8 is indeed 8. So we are good here, and this truss is statically determinate. If we had a truss that was, say, not statically determinate, say maybe this was a pin support instead of a roller, then we have a situation in which internal forces, so like this load would cause a bending. So this beam would want to bend right here along this path, and that would the pins would be locked in place, and so there would be internal stress in the beam that we would not be able to account for in this method of solving for the truss forces. So we want to make sure that we're statically determinate, and once we determine that we are, then we can go ahead and move forward here into our steps for solving a truss. So the first thing that we do, and again, I'm doing this simply from an organization standpoint, just to make sure that A, we have all of our answers in one place, and B, it's easier for you to grade for your students. So what I'm going to do here is just kind of set up a free body diagram, okay, and this is where I'm basically just going to place all my answers. So I'm just going to draw in the joints. Okay, and then I'm going to color code this. So any member that is on the inside, I'm going to represent, for right now I'm just going to put a line on it just to represent that the member is there. But I'm not going to put any arrows or directions on this until we figure out if this particular force is in tension or compression. Okay, and actually let me take those out. So our internal forces here are going to be represented in blue. It's just our different members that we've got here, and we'll go ahead and label this as well. So this is A, this is B, and then we've got C right here, and then we've got D over here. There we go. All right. Then so we're calling the blue the internal forces. And then the external forces I'm going to put in red. And the external forces are any load that is on the outside of the truss. So the reaction, so the pin and the roller, they're on the outside. Okay, and then we also have the only known load at this point, which is the 500 pounds that's being applied to the truss. So we're assuming that this truss is in static equilibrium, and so we're going to be using static equilibrium equations to solve for the entire truss. And since we assume that the entire truss is in static equilibrium, we can use method of joints to isolate each joint and assume that since the whole system is in equilibrium, that each individual component of that or each individual joint is also in static equilibrium. All right, so moving forward here, you'll see that number 1 says solve for all unknown angles and draw the master free body diagram. And so you can see I've already put the angles in up here. We've got 56 degrees at joint A and then 45 degrees at joint B. All right, and so we're going to kind of check that one off. We're going to say we're good there, and we've got our free body diagram drawn, and we're going to, as we get answers, we're going to update this. The next thing that we're going to do is we're going to deal with these forces in red. Okay, so we want to solve for the external forces, meaning the reaction forces, and the first one we're going to deal with is the roller. Okay, we're going to say that the pin support is going to be our point of rotation, and that the 500-pound load is going to cause the truss. The truss is going to act as a single unit, right? It's going to act as a system. So when this 500-pound load is applied, the entire truss wants to rotate in the clockwise direction, and then something has to stop that. Something has to stop the rotation. So the reaction force here at D is going to be pushing in the opposite direction in order to prevent that from rotating. So that's the first thing that we're going to do. And to do that, we're going to use the equations here. You'll see they're kind of just to the right of the screen. Okay, the equation is the sum of the moments equals 0, and a moment is a force times I don't have the symbol in there, but a perpendicular distance. So a couple things we need to clarify here. We need to decide what is positive and what is negative, because if they're going to balance out, then direction matters. So we're going to say that that clockwise, so I'll put this up here, we're going to say clockwise equals negative, and that counterclockwise equals positive. Okay, so if we go back here to our setup, this 500 causes a negative moment, and then we don't know because it's an unknown at this point, so we're going to assume that it's positive. Anytime we don't know, we're going to assume it's positive. And then if the answer comes out positive, we were correct in our assumption, and if it comes out negative, then we were incorrect in our assumption. So so logically, you can probably tell from just looking at it that if this one's going 500 down clockwise, then we need to do counterclockwise to counter that. But again, we're going to let the math play it out. Okay, so so knowing that, we've got the sum of the moments equals 0. That's going to be our equilibrium problem. And then a moment is a force times a perpendicular distance. So 2a, we're going to, so we'll put 2a. And then we're going to do the sum of the moments equals, and what I need to do is find every external force and account for that. So a moment being force times a perpendicular distance, we have this, we'll call this the reaction force. We'll call this the reaction force at A in the y direction. We'll call this the reaction force at A in the x direction. And this one will be the reaction force at D in the y direction. So we know that if a force, or if a moment is a force times a perpendicular distance, the distance between RFAX and RFAY to the point of rotation is 0. So that automatically eliminates those from our equation, because whatever the force would be, it would just be times 0. Okay, but 500 is located a little bit of a distance away from that, and so the force is going down, so the distance would be perpendicular to that. So therefore, the distance here was 2. So if we go back and look, you'll see we've got it 2 feet away from the pin. So the moment is going to be, the moment created by the 500 pounds is simply going to be 2 feet times 500 pounds. All right, that's the moment. And then the direction is clockwise, so we're going to make that negative. Then, so that's our first moment that is created. And then the second moment is whatever it is going to be that's stopping that, which is going to be the roller support. So so again, I'm going to assume positive, so we're going to add, and we're going to say the distance from the roller to the pin is 5 times the force, and I don't know the force, so we're going to put in RFD y. So it's the reaction force at D in the y direction. We don't know if it's clockwise or counterclockwise, so again, I'm just leaving it positive, and we're going to say the two of those summed together are equal to 0. All right, and so when I do that, I end up with negative 1,000 plus 5 RFDY equals 0, and so that would be 5 RFDY equals 1,000, and when you divide that out, we get that RFDY equals 200. So in fact, it did come out positive, like we expected, and so that means that this is going counterclockwise. So we can go ahead, I'm going to erase out this here, and I'm going to update our little diagram, put this in red, and we'll say that we know that that's pushing back up, and we know it's pushing up at a value of 200 pounds. Okay? All right, so again, we're going to use that pin support as our point of rotation, and we're going to sum up the moments and set them equal to 0 to solve for our roller support. The next thing that we're going to do is look at the pin support. Okay, so we've got these two unknowns right here, and we have to finish out our red ones, our external forces, before we can look at the internal forces. So the two red ones, again, we said earlier that we're assuming this truss system is in equilibrium, and we used the sum of the moments to get the 200 over here for the roller. So since the entire system is in equilibrium, we can use the regular static equilibrium equations to solve for this one. So we've got the sum of the forces in x equals 0 and the sum of the forces in y equals 0. So I'll go back to this here, and so 2b is saying that basically whatever I have going up, I have to have going down. Whatever I have going left, I have to have going right. So in this case, we'll start with the y direction. We'll say that the sum of the forces in y for the entire truss is, I've got 500 going down, I've got 200 going up. So let's say 200, and then that's positive. 500 going down in the y direction, so minus 500. And then I've got RFA, which is in the y direction. I don't know if it's positive or negative, so I'm going to say plus RFAY. And then I've got RFAX, but that doesn't have a y direction, that's in the x direction. So we'll set those two equal to 0. Okay, so when I solve for that, what ends up happening is these two come out to a negative 300, so it would be negative 300 plus RFAY equals 0. So RFAY is equal to 300. Okay, now notice these are not moments, right? We're done. Once we finish with 2A, we're not dealing with moments anymore. We're dealing with the entire system in x and y. So if I have 500 going down, I have to have a total of 500 going up for this truss to be in equilibrium. So, and if you just look at that, that kind of makes sense. 500 down, I've got 200 up. What's left? Well, that's going to be 300. So we're going to take out this here, and we're going to put in 300 right there. Okay, so now we have solved for the y direction. So now we need to deal with this RFAX, and we know that we know that the sum of the forces in x, so let's I'll try and put that one right, let's put it right here. We know that the sum of the forces in x equals 0, and so if that's the case, we only have one x force, so we've got the reaction force at A in the x direction. It has to equal 0 because there's nothing to counter it. Okay, so and just keep in mind, your students may ask, like, why is it 0? And that's just simply means that in this particular loading configuration with just a 500-pound load in the y direction, we don't have anything in x, so therefore the pin support is not having to push back in the x direction to either push or pull to oppose another force in the x direction. If, say, a car were to hit the side of the bridge, then an x force would be introduced, and then the pin support would have to counter that. But in this particular loading configuration, there is no value in the x direction. All right, so once we have our external forces done, we can now move into the internal forces. And so we can check off number 2. We solved for the roller reaction. We solved for the pin reaction. We're done with all of the red. Okay, so now we're going to go into the blue, and we're going to solve for the internal forces using method of joints. And again, we're going to have those same two equations, the sum of the forces in x equals 0 and the sum of the forces in y equal 0. Now, the one thing that we're going to have to define here as we start looking at these, and we've already done this a little bit here, we've got some different arrow directions, but we need to just specify what these arrow directions are actually saying. Yes, that they do mean that they are, like for the 300, it is pointing up in the y direction, so therefore it is y positive, and then the 500 is y negative. Okay, but it also means, and I don't want you to confuse these, but it also determines what is in tension and compression. So for example, if we were to have an arrow that points away from the joint, then we're going to say that it's pulling on that joint, so therefore the joint is in tension. Okay, and then if we were to have an arrow that is pointing to the joint, then we would say that the joint is in compression. Okay, so that's just something to keep in mind a little bit later. But the reason that I bring that up now is because when we go into the method of joints, we have a lot of unknowns here. And so when we have an unknown vector, we're going to assume that it is in tension, and then if the answer comes out negative, then we know that our assumption of the member being in tension is incorrect. Now, I don't want you to confuse that with x and y. Okay, sometimes when we assume tension, it might be pointing up. Sometimes when we assume tension, it might be pointing down. That doesn't matter. We'll still treat it as y positive or y negative, but you'll see what I'm talking about here shortly. Okay, so the method of joints, what this allows us to do is it allows us to isolate certain joints, and we'll do this strategically. We're going to isolate one portion of the truss, and we're going to solve for that and get it in equilibrium. And then once we have that information, we can move to the next joint and so on and so forth. So what I'm going to do here is I'm going to be a little bit strategic about which one of these joints we're going to start with. A, you can see, has two unknowns. It has the AC is in the x direction. AB, since it's at an angle at a 56 degree angle, it has both an x and a y component. So that tells me right there that AC has a y component and AB has a y component. So that's two unknowns I can't solve for. Or I'm sorry, AC has an x component and AB has an x component. So that's two unknowns in x. But in the y, AC does not have a y, AB does have a y component. So therefore, that's a single, we can solve for that. So this would be, A would be a good joint to start with. D would also be a good joint to start with because, again, same thing. We have two x components, but then we only have one y component, being BD is the vector there, the member that has the y component. C is not a good choice because we don't have any information related to x. So I've got two unknowns in x. And then B has three different vectors, so this is not a good choice. Too many unknowns there. So we're going to start with, let's just start with A. So I'm going to come over here and we'll write these in blue. I'm going to bring joint A all the way over here. And we're just going to kind of blow it up a little bit so that we can figure this out. So I'm going to draw these vectors a little bit bigger. And again, I don't know if they're in tension or compression. So I don't know if they're pointing up or down. So what I'm going to do is make them in tension. So that means I'm going to put an arrow pointing away from the joint for both of them. We know that the magnitude of this vector is the force of AB. It's an unknown. And then this one would be the force of AC. Okay, but I do know that I have 300 right here. Right, we do have that from our pin support. We also have a 0, which I'm not going to show on there because it doesn't affect the system. So finally, we have our angle, which was 56.31 degrees. We'll label that in there as well. All right, so now what we're going to do is we're going to focus on the static equilibrium equation. So the sum of the forces in x equals 0, sum of the forces in y equals 0, and we're going to solve for this. So we have FAC is in the x direction, FAB has both, and when I say that, I'll put a little line here to show you here. FAB has an x component. Any vector with an angle here has x and a y component. So we're going to have to use those. We'll have to solve for both of those. But since there's two unknowns for x, we're going to have to start with the sum of the forces in y. Okay, so I'm going to write the equation here. We're going to take anything that has a y component out of joint A, which in this case would be FAB and the 300, and we're going to sum them up and set them equal to 0. So I'm going to sum the y's, set them equal to 0. So first off, 300, it looks like it's pointing up, so that means it's positive in the y directions. So I'll say the sum of the forces in y is 300. And then it also looks like FAB seems to be pointing up in the y direction. So we need to get the y component out of that vector. Okay, because if I got 300 going up in y and this one's at an angle, the vector's not going to be 300. But the y component of the vector will be 300 because they have to balance out. So to get that y component, and again it looks like it's pointing up, so I'm going to say it's positive. So it's 300 plus, it's going to be the sine of 56.31 times the magnitude. So to get the y component, we take the sine of the angle times the magnitude, or the hypotenuse there, so that's going to be times FAB. Those are my two y components. Set them equal to 0. So that's going to bring this over to the other, 300 over to the other side. So we're going to get the sine of 56.31 times FAB equals negative 300. And then what we end up with is FAB equals negative 300 divided by the sine of 56.31. So FAB, when it's all said and done, comes out at a negative 360, so negative 360.56. All right, so this answer came out negative. All right, so that doesn't mean it's a negative force, but what it does mean is, again, I chose the direction of the arrow, meaning I chose tension pointing away from the joint, and since this came out negative, I know that my assumption of it being in tension is incorrect. So this one here is actually in compression. Okay, so that means if I can go back here and I can say, oh, that's actually wrong, and that means it actually in reality points down like this, and we know that the value of that is 360.56. Okay, so I'm going to go up here into my larger free body diagram, and I'm going to go ahead, I'm going to write this in. So if AB is 360 at joint A, then it's also going to be 360 at joint B because it's the same member. So I'm going to put in 360.56, and then I'm going to put a little C underneath just to show that it is in compression. And since it is in compression, you can see that the arrow should be pointing to the joint. So I'm going to put an arrow here, and I'm going to put an arrow here. Okay? So that solves that particular joint right there. So now we have one more. We have FAC that we need to solve for. And again, we assume tension, so it's pointing away from the joint. We did fix this one, so we need to pay attention that we're using the correct direction in X, because this time we're going to be doing the sum of the forces in X. So I'm going to change colors here, and we're going to go ahead and try and squeeze this one in right here. So we're going to say that the sum of the forces in X equals, and it looks like FAC is in the X direction, so there's no angle, it's horizontal. So we're going to say that FAC is one of our X components. And then we know that FAB has an X component. Okay, so but it looks like it's pointing to the left. Right now it's pointing to the left in the X direction. So that would be negative X. So I'm going to say negative, and we have to get the X component out of this. So to get X, we're going to use cosine. And we're going to say the cosine of the angle, so it's 56.31. Okay, and then we're going to multiply it by the magnitude. Now we know the magnitude is 360.56, and then we're going to set all that equal to 0. So now we can simplify, and what we end up with is this goes to the other side. So we end up with FAC equals, and our answer here is 200. All right, so now that actually means that it is in tension, okay, because it came out positive. So we assumed FAC was positive, so therefore we've got, we were correct. It came out positive, so came out as, we assumed tension, and it came out positive, so it is tension. So FAC is 200. So we're going to go up here, and we're going to put this in as 200, and it's in tension, so it's going to have to be pointing away from the joint, and same thing over here, it'll be pointing away from the joint. All right. So because the entire truss is in static equilibrium, we can pull A out and solve for the vectors here, and solve for the members, the forces here, and assume that they're in static equilibrium as well. So that's why we're using our sum of the forces in X equals 0, sum of the forces in Y equals 0. All right, so we finished joint A, and we were able to get 2 out of our 5 members. So again, we're going to be strategic. We have a nice opportunity here for joint C. Anytime you see joints that are they all have 90-degree angles, either they're vertical and horizontal, that's perfect, because that just means if the sum of the forces in Y equals 0, if I have 500 going down, I have to have 500 going up, right? So this is a really easy one. We can actually write, so I'll put C here. And then we've got this force we don't know, so we're going to assume tension. And this is the force of BC. We've got this one, which we do know, is 200. We've got this one that we don't know, so I'm going to assume tension. So this is the force of CD. And then we know the 500 that's going down, 500 there. So if we were to use our static equilibrium equations, again, let's start with Y. It would be the sum of the forces in Y equals, I've got a negative 500, and then FBC is in Y, and it looks like it's going up. So it's going to be plus FBC equals 0. So that means 500 is going to go to the other side, and FBC equals 500. So this is 500, and again, I just showed the equation, but you could pretty much look at that joint and just say, oh well, 500 is going down, 500 has to go up, which means it's in tension, so that means this one has to be pointing away from the joint at B there as well. So 500, 500, and you can probably guess what this is, FCD. It's going to be 200 pointing to the right, so in tension. So we got the sum of the forces in X equals, I've got negative 200, meaning 200 is pointing left, pointing negative X. So negative 200 plus FCD equals 0, so FCD equals 200. So we'll update this one, 200 going to the right, and then that would tension. So I'm going to go back and just put a little T under all of these just to show that those are in tension. And then look at that. We're left with one additional member to solve for. Okay, and so again, now we have really only one unknown. But if I do, so I can choose either joint B or joint D to solve here. But if I do B, then in the Y direction I have this AB has a Y component, 500 has a Y component, and so does BD. So that's 3 vectors I got to deal with. Whereas if I just chose joint D, the only thing that I have is the 200 in the Y direction, and then BD has a Y component. So it would just be 2 to deal with there. So I'm going to choose D because it will be a little bit easier. And then we're going to go ahead and just bring D down here. So this time, okay, we're going to assume tension. So I don't know what the force of BD is, but I'm going to assume that it's in tension, which means it's pointing away from the joint. So in that case, it's positive. I'm assuming positive Y, and I'm assuming negative X. But we will let the math figure it out for us here. Okay, we've got the 200 going to the left here, and we've got 200 pointing up here for the reaction force. And we know this time that this is a 45-degree angle, so that's going to affect our, make sure that we use the right angle for that. Okay, so all right, so all I have to do to solve for this one is use the sum of the forces in the Y direction equals 0. So I have a 200 going positive, so I'll say 200, that's in the Y direction, so just 200, plus, and then FBD looks like it's pointing up, so we're going to get the Y component of FBD. So the Y component is going to be the sine of the angle, so the sine of 45, times the force, FBD, and we're going to set that equal to 0. So what we end up with is the sine of 45 times the force of BD equals negative 200. And then when we solve that down, FBD equals negative 282.84. All right, so 282, kind of looks like a 4 there, but 282.84. So we'll write that in, 282.84, and we're going to put that up here in our free body diagram as well. So I'll put in 282.84. That ended up being negative, so that means that this one, we assume tension, came out negative, so it's actually in compression. So that means that arrow is going to be pointing to the joint, and we're going to write our little C underneath right there. So congratulations, we have finished our first little simple truss using the method of joints. So just to recap a few things, number one, we're going to make sure that the truss is statically determinate using 2j equals m plus r. We're going to create our little free body diagram here that we can kind of put all of our answers. And then we're going to start by solving for our roller support using the sum of the moments equals 0, and then our moment equilibrium. And then we're going to finish out external forces with the pin support using the sum of the forces in X and Y equals 0. And then finally, we're going to use the method of joints and isolate each joint and do equilibrium equations on that. All right, so now let's go ahead and check our work here. So I'm going to go out of this program, and you can see and what I'll do is I will create a new truss that is exactly the same as this, but this is using MD solids, and I'm just going to click on new truss. We're going to set our spacing intervals to 1 and 1, and I just gave myself 5 spaces in both directions. So we'll hit OK. We're going to hit create, and then I'm creating members, so I have to draw each member out. So I can't draw all the way to 5. I have to draw, this would have been what, AC. Okay, so that is 2 feet long. The next one is 3 feet long. This one went up 3 feet. And then, so there's our 56.31, there's our 45, and we have the truss. If for some reason you need to erase a member, you can click erase, and then you have to actually just redraw it. So if I redraw it, you'll see it goes away. So I'm going to put that back in. All right, we can only put loads on the joints, so we have to pay attention to that. And so I'm going to go ahead and put a load on, and the load goes right here. And it says downward direction, so that's what I want, 500. Enter the load. Usually you can just like click and drag down and let go, and then that's how the load would be placed. Same thing, if I want to erase, I click and drag down, and then that is gone. So create, click, drag down, let go, 500, enter load. Same thing with supports. So I'm going to create a support. The way that the supports are put in here is you draw the reaction force. So for example, if I click here, this is a roller, I know that I have one reaction force in the Y direction. So I'm going to click, drag down, let go, and you'll see I have a roller. So over here, if I click, drag down, and let go, I have another roller. So I'm going to add another, this time I'm going to add the reaction force in the X direction. So I'll click and drag left, and now it turns into a pin. So we've got a pin, a roller, a load, we've got all of our members, and we're going to hit compute. And so when we hit compute, you'll see that we have 360.56. I believe that's what we came up with here. 360.56. We've got 500, 200, 200, and 282. And you can see that the orange represents compression. So we did get compression on ours for the 2 outer members, and then everything else was in tension, which is the blue. So this is a great way to make practice problems. It's a great way to check your work. But anyway, it's a great program using the Truss module in MD Solids. All right, so here's another example that we're going to do. This one's just set up a little bit differently. So the first truss we did was like on the ground. Second truss, this one is going to be mounted from the wall. So we've got a pin support at the top. We've got a roller on the bottom here. So this is again mounted like a chin-up bar here. So it's mounted to the wall, and then we have a load here of 75. So the first thing, so we're going to go ahead and solve, do the same process here. This one will go a little bit quicker. But first thing we're going to do is our static equilibrium, or I'm sorry, statically determinate equation, 2j equals m plus r. So to determine, we have the number of joints, so j, 1, 2, and 3. So we have 3, let me go here to brushes. Sorry, we have 2 times 3 equals the number of members. I have 3 members here. And then the number of reaction forces, I've got a pin and I've got a roller, so 2 for the pin and 1 for the roller. That's going to give me 3. So again, pin is going to give me a reaction force in the X direction and the Y direction, and the roller in this case is going to give me a reaction force in the X direction. So 2 times 3 is 6, which is equal to 3 plus 3, so 6 equals 6. So we are good to go here, and we can go ahead and move forward. So we're going to go ahead and again stick with our colors here. We're going to do our free body diagram. So I'm going to start by just kind of drawing the bigger one in. So we'll do our joints, so 3 joints. We're going to use our blue to do the internal members. So I'm not going to put any arrows on those yet because I'm just not sure what those are going to be. We're going to let the math work that out. And then, so there's my internal members, just the actual members. We can even go ahead and label those. We'll call this one joint A. We'll call this one down here joint B. then we'll call this one here joint C. So we've got A, and actually I'm going to move that out of our way. I'm going to put this over here a little bit. No, that's in the way too. A, and then I've got B down here, and then C over here. And then in red, we're going to do our external members. So again, I know that the pin has a reaction force in the X direction, and it also has an X force, or I'm sorry, a Y direction, a reaction force in Y. So we'll put one here, and then for the roller, it's only going to be an X. And then we also have the 75-pound load, that's external as well, and that one has a direction there, so 75. Okay, once we do that, we need to solve for angles, which you can see we already have an angle. So I think we're good on everything that we need to know for this particular truss. One thing I will say is make sure with your students, like you might get some students that are tempted to use this angle here. Make sure that you're always using the angle. If you're going to stick with sine being y and x being or cosine for x and sine for y, then they need to be using the angle relative to the x-axis. That will keep sine solving for the y component and cosine solving for the x component. So again, it's just a little bit of consistency there, and that'll help students avoid some confusion. Okay, so the first thing that we're going to do is we've already got solve for unknown angles and draw the master free body diagram. Solve for external forces. We want to start by solving for the roller support. So this 75 pounds, right, is 75 pounds causes a clockwise, which we know is negative, causes a clockwise rotation about the pin support. So the truss wants to, rotate towards the wall, but then the pin is like, or I'm sorry, the roller support is like, no, I'm not going to let you do that. I'm going to push back. So we're going to get a reaction here at the roller support. All right, so we can label those. We've got the reaction force at B in the x direction, and then we've got the reaction force at A in the x direction, and the reaction force at A in the y direction. Okay, so those are the three forces that we're trying to solve for. So the first one we're going to deal with is the roller. So if our point of rotation is A, then we have to use the sum of the moments equals 0. So I'm going to put that right here, and we'll change colors for this. We'll go with this. Okay, we'll say that the sum of the moments equals, remembering that a moment is a force times a perpendicular distance, and this is where people get tripped up a little bit. You have to remember that it's all perpendicular distance. Here we have a rotation point all the way out here, A, so the perpendicular distance would be this direction here, and you can count the lines. Each line represents 1 foot. So in this case, this distance from the pin to the roller is going to be 1, 2, 3, 4. All right, and then this one is going to be 3, so we can figure that out. All right, so the sum of the moments, we know that we have the 75 pounds causing a rotation about A. So that one is going clockwise. It's going to cause a clockwise rotation. So that's going to be 3 feet. That's the perpendicular distance to the pin, right? So 1, 2, 3. Doesn't matter that it's down here. It's perpendicular. So 3 times 75. And since it's going clockwise, causing a clockwise rotation, we're going to make that negative. Then the next thing we have is B pushing back, right? So the roller is going to be stopping that rotation. So we're going to say plus, and then what is the perpendicular distance there? Well, it's going to be 1, 2, 3, 4, right? So that's going to be 4 times the reaction force at B in the x direction. Okay, so there's our 2 moments. Set those equal to 0, and so we end up with, so we got 225, so we got negative 225 plus 4RFBX. Okay, and then, so if I were to move that to the other side, we got 4RFBX equals 225. We divide that by 4, we get RFB, that should be X, not Y. RFBX equals 56.25. Okay, and notice that it did come out positive. We assumed positive, right? So right here we assumed positive, and when we're solving for moments, positive means counterclockwise. So therefore this came out positive, so our assumption was correct. This is indeed going counterclockwise. So that's good. So that tells me then we can go ahead and do some updating here. We'll get rid of that label, And then we're going to put, so this, in order to counter the 75, it has to be pushing back in this direction, 56.25. Okay. So then that leaves us with two additional reaction forces up here that we have to solve for. And so for number 2, D or B, it says solve for the pin reaction using, and then the two equations that we're going to look at again are the static equilibrium equation. So it's the sum of the forces in x equals 0 and the sum of the forces in y equals 0. So we're going to use that to solve for these two remaining forces. So, and again, we're looking at the truss as a whole. So if I look at what I have here in red, the external forces, I've got 75 down, I have to have 75 up. And if I look at all my other external forces, there's only one place that I have another y component, right? So 75 here is down in y, I have to have 75 up in y. So that means that this here, RFAY, so the reaction force at F, or reaction force at A in the y direction has to go 75 up, right? So 75 up in y. And the same thing is true here. We got 56.25 going right, so that's going positive x. I have to have something countering that, so it has to be 56.25 going left for this one here, which is, it's both a little surprising, like students will say, oh man, why is that going left? How's that working? And it actually makes sense, because if the 75 is causing a rotation in this direction, then what it's actually doing is it's actually pulling this off the wall, right? So the wall is actually having to pull back and keep the truss from, pulling away from the wall. And then the bottom, the roller, is keeping it from, smashing into the wall, like damaging the wall. So the wall is pushing back down here, but at the top it's pulling. So we've got opposing forces there. But overall, the truss is in static equilibrium. So, so we solve for those two, and now we're going to move into the internal forces, our blue forces here, using method of joints. So I'm going to switch over to blue. We're going to decide on which one of these joints we want to solve for. I could do A, I could do C, but honestly C has fewer members, so I'm going to choose C. So again, just like last time, it looks like BC has only an X component, which means that I can solve for AC using the 75. So that's a good one to start with. So I'm going to bring C out here, and we're just going to draw the joint. I'm going to draw the first member. This is, and again, I'm going to assume tension. So that's just pointing away from the joint, which happens to be positive y and negative x. And that's going to be the force, is going to be the force of AC. Okay, and then the one here, we've got another one. I'm again assuming tension, and this one is going to be the force of BC. And then finally, we know we have the 75, and we know its direction. It's 75 going down. So negative y. All right, so we're going to have to use, so we have two x components, two unknowns for x. So we're going to have to use y to start with. So we'll do the sum of the forces in y equals, I know I have a negative 75, and I know that we're going to have this y component here. And that's essentially what we're saying. Like we did over here earlier, we said 75 down, 75 up. Same thing here. I've got 75 down, I have to have 75 up. So that means that this right here, the y component for FAC has to be 75, right? So we're just kind of like using the component equation along with static equilibrium to get that what is FAC if the y component were to be 75. So so having said that, we'll put in, how do we get the y component for FAC? It's going to be sine of the angle, so 53.13, and then times the force, right? So FAC is the force, we don't know what it is, it's unknown. That's our y component, and then for FAC. And then we're going to add it to the y component for this vector here, which is negative 75. So it's going to be minus 75, or you could say, since this is the sum, you could say plus negative 75, same thing, and then equals 0. So when we work that around, 75 goes to the other side, and so we end up with FAC being equal to 96, so equals 96.75. All right, and you'll notice that it did come out positive. We assumed tension, and it did come out positive, so this actually is in tension. All right, so that's good. It's pointing up, and we assume tension, which means it's pointing up. This one's pointing down. Looks like it makes sense. So 96.75 is our answer here. So I'm going to put that in, 96.75. Point that one up, point this one down. Again, it's not about up or down, it's tension or compression, which is either pointing to the joint or away from the joint. And so tension points away from the joint, so it's tension there. All right, so we got 96.75, and now we've got this FBC that we need to solve for here. So we're going to use the sum of the forces in X to solve for that one. Okay, we know that FBC is in the X direction, so there's no like sine or cosine here, it's just FBC. And then we know that FAC also has an X component, and it is pointing up and to the left, so the X component would be negative. So it's going to be the cosine of 53.13 times, and it's going to be the whatever we got for FAC, so this was 96.75. So it's going to be the cosine of the angle times the magnitude, and that's going to give us our X component. So it's going to be cosine of 53 times cosine of 53.13 times 96.75. All right, and then so that's our Y component for, I'm sorry, X component for FAC. Then we've got FBC, which appears to be going left. By the way, this one was also going left, so that's going to have to be negative. So this one would be minus FBC equals 0. And so when we simplify this down, what we end up with is that FBC equals, and if we simplify this there, it's going to be negative, again, it's going to be negative 56.25. Negative 56.25. So that tells us that, again, our assumption here for FBC was tension. It actually is going to be in compression. So it's actually, we're going to have to turn this arrow around here, and it's actually going to end up going the other way. So, so this is going to be 56.25, and that means this is in compression. Okay, and that actually, if you look over here, it works out pretty well, right? So if this is 56.25, that means this is 56. So these two are balancing each other out, and then over here, these two are balancing each other out as well. So we've got 56.25, 96.75, and we're left with this one member right here. So if we were to bring B down, and we know that this is 56.25, this is 56.25, and we have one member left. There's nothing to oppose it, so it is 0. So that's nice and easy to do there. And so, so that is what we would refer to as a zero force member. And in a zero force member, so kids will, a lot of times will say, well, why don't we just get rid of it? We don't need that. But we do need it from a stability standpoint. And again, it's only 0 because of the current loading configuration. So we've got 75 down here, and the way that, the forces are distributed, this particular member is carrying nothing. But if we were to say move a load to here, you know, to pointing down here, then all of a sudden that would be carrying a lot of load. So again, this is just the configuration that it's in. In that particular case, that is not bearing any weight. But from a stability standpoint, if we didn't have it there, then this roller would just roll away, right? This member here would end up kind of rolling down the wall like so. So we need it, and it would just kind of collapse in on itself. So we do need that member from a stability standpoint. Again, if it wasn't there, we would not be able to satisfy the 2J equals M plus R, so it's no longer statically determinate. By the way, we kind of went the long route on this one, but we could have easily pulled B as our first joint, because once we solve for the roller support, because again, it would have been 56.25, and then we didn't know, right? So if this one's got 56 going right, then this one has to be 56 going left, and then this one had nothing to oppose it, so that has to be 0. So that is like, we like when we see joints like this. So these are easy to solve for, and you don't have to go through all the sine cosine. But this also shows that even if we do go through the sine and cosine, we still get the same answer, right? So negative, in this case was negative 56.25, giving us compression for this particular member there. All right, so hopefully that helps. Feel free to reach out with any questions, comments, or concerns, and I would recommend doing some practice with this as well. And let's just go ahead and real quick verify. So if I go here to MD Solids, we said that the member was, so 1, 2, 3, 4, 1, 2, 3, and then we connect those two, so 53.13. We'll put in our support, so there's a roller, one reaction, and then another reaction. That makes that a pin. Load, click and drag down. I said 75, enter, and then compute. And so there it is, 93.75, and then we've got 56.25. So it looks like we're in good shape. So, all right, if you have any questions, please reach out. Hopefully that was helpful, and we'll talk to you soon.